All right, so the last class we had sort of touched very briefly on derivatives and what happens when you do a derivative of a logarithm, in particular a natural logarithm. And we discussed this idea that how a log is actually defined as an integration of the value 1 over x. So that means then that the derivative of the log is actually the function 1 over x. And we did a couple of examples, I believe. We did one like this that was very straightforward, nothing to do because the chain rule actually had an inside function's derivative of 1, and so it was very uninteresting. But then we had a legitimate one that we dealt with that was a little more involved. And we looked at it and we said, okay, well, that's kind of a mess to start with. It might be easier if the first thing I do is to separate that out using some properties of logs, take my derivative, and then we have to actually put it back together as a single function, so a single fraction. And we ended up with this particular derivative at the end. So we're going to keep working towards that and taking a look at this one today. All right, so on this one, we have the natural log of x plus the square root of 4 plus x squared. And the unfortunate thing in this case is, as much as I would love to have some kind of a log property to separate those, I don't, because of the addition, right? If it were multiplication, we'd be good to go. We'd have all sorts of beautiful separations we could make, but we don't. We have addition. So the best we can do is to simply start with chain rule, right? All right, so what is the antiderivative, excuse me, I'm already ready for 6.2 or 5.2. What is the derivative of a natural log? So we just mentioned this. What happens when I have a natural log? 1 over whatever's inside. So if it were a natural log of x, it'd be 1 over x. So in this case, I'm going to have 1 over, and I'm going to have x plus the square root of 4 plus x squared, right? And that's the easy part, because the other part is actually the chain rule of the part inside, right? So the first part of it's not so bad. So what's the derivative of x? 1, yeah. But then I need the derivative of square root. Do you remember how we deal with the square roots when we're doing their derivatives? Right. We want to remember that this can be expressed as 4 plus x squared to the 1/2, right? All right, so what's its derivative? You're going to have a 2x. I usually put it at the end just because the way we wrote up our chain rule. But yes, there is going to be a 2x. Right, so you've got a power rule, so you're going to bring the 1/2 down. Make sure you rewrite the inside exactly like it was. What will the new exponent be? Good, negative 1/2. And then Parker, here's where you're remembering the 2x. And where does 2x come from? Right, the derivative of the x squared. Well, actually, it's the derivative of 4 plus x squared, but yeah. Yep, look good? So again, if you were doing the basic skills test, right, when we do that, you'd be done. And how wonderful would that be? But we're going to simplify these as well. You guys are going to get great at your algebra. I think I told you that last time too. So let's take a look at simplifying here. So somebody tell me one quick simplification I could do. We could do that. There's even one that's even quicker than that.
Cancel the 2.
Yeah.
1/2.
This 1/2 and this 2 could simplify. That's kind of nice. And while I could put that on the top, if I do that, the problem I'm going to have is now I'm going to have a negative exponent on top, which might not be so good. Does that make sense? Because if I move the second part simply to the top of the fraction, now I've got to deal with the negative exponent. And because there's addition within there, I can't just pull it straight down. So I'm actually going to rewrite it where it is out to the side. So I'm going to write this as 1 over. This is x plus the square root of 4 plus x squared. And then I've got times. So I've got 1 plus, I've got x over the square root of 4 plus x squared. Okay. Is that okay so far? What else could we do? because we certainly can't be done. Can we do what?
Common denominator.
Yeah, I think that's a good next step. So this 1 here and this fraction here, let's just combine them, and beautiful things are going to happen when we do. So it's a really good suggestion. So let's take a look. We got 1 over the x plus the square root of 4 plus x squared. And then I'm going to actually have a 4 plus x squared now that's on top because of the 1, right? 1 is going to be that 4 plus x squared top and bottom with the square root, of course, plus my x, and my denominator is the square root of 4 plus x squared. Does everybody see where that all came from? Does everybody see why that's really nice? Yeah, what's really nice? What can I do?
Cancel out.
Yeah, that top right there and that bottom right there, they match. And that's great because they simplify then and they reduce. So my actual expression, the final derivative, is actually going to be what? Good job. Any questions on that one? All right. This right here is not going to look any different, but I want to introduce to you the idea that if you have an absolute value, the derivative, when you've got the absolute value around the inside, remains the same. That is, if f of x equals ln of absolute value of x, then the derivative f prime of x is still 1 over x. It doesn't change anything. So if we take a look at the next example, we're actually going to see some absolute values there, and we'll talk at the end about why they're necessary. But for practical purposes of working through the derivative, they don't affect us. Okay? So what will my derivative be of the natural log of the absolute value of sine x? 1 over sine x. Good. And then the derivative of sine x is cosine x. And you definitely don't get to leave it that way. We can simplify it from the get-go and write it as cosine x over sine x. That would be fine. Which is, which one? It's cotangent. That's cotangent of x. Sine over cosine is tangent, so cosine over sine is cotangent. I want to make one mention then here. It says at the bottom, why must the sine x be in absolute values? There's actually a really good reason why it has to be here. Do you remember our function log, like its graph that we did last time? What input values, what domain values was I allowed to have? Positive, right? It was only on the right-hand side of the y-axis, only positive input values. What do you know about the output values of sine? What can sine values be?
Negative.
They could be negative, right? In fact, they oscillate between -1 and 1, right? They go back and forth. Remember, in the sine graph, it goes just up and down. It does this wave kind of a pattern. So we need those absolute values there to eliminate the negatives. Now, that doesn't eliminate all the problems because it still can't have the sine values that come out as 0. But I couldn't have had those with logs anyway. So that's not a huge deal. We're not asked about the domain here. I just want to mention to you why you actually have the absolute values. All right. Yes, Parker.
I was wondering, why do you multiply it by cosine x? Forgot.
Okay, so who was it that told me it was there? Was it you, Chelsea?
Yeah,
So why did we multiply by cosine x?
because you have to take the derivative of the whole thing, and then you have to take the derivative of the inside first.
Right. And then the derivative of sine x then was cosine x. So that's where that key piece came from. It's a chain rule. It was coming from the chain rule. Good question. Okay, we're going to take a look then at a function that has a portion of it that's a polynomial, 3x squared. We've also got a log inside of here. The directions here are a little bit different. They don't simply just say find the derivative, although we're going to do that. They actually ask us to find an equation of a tangent line through a point, which starts to sound a lot like something you probably did last semester. You found some tangent lines, didn't you? And in order to find a tangent line, do you remember the pieces of that process? Okay, so somebody tell me what you remember. You need the slope. And how do you get the slope? By the derivative, right? Evaluate it at whatever point you're given. So we do our derivative, and we're going to evaluate it at a specific point. In this case, the point x equals 1. And we could use y equals 3 if it were necessary. It won't be on this one because of the way the function is defined. So we're going to start out by taking the derivative. So what is the derivative of this function? 6x minus 1 over x. Great. And then we're going to evaluate it at x equal 1. And what are we going to get? 5. And just like was mentioned, this then is the slope, right? Okay, now I've got a slope, and I have a point. Do you remember what I do when I have a slope and a point? This is algebra now. You can. There's a couple of ways you can do it. You can do y equal mx plus b if you'd like. There's another one. Y minus right. Either of those will work. If you want to use the slope-intercept, the way you do that is you put in the 5 in for m. You put the x and the y in that you were given, and you'll solve for b. You can do that. Or you can plug it in directly, and then you have to write the answer with the m and the b plugged in. Or you can do it directly from here, and then there's no rewriting when you're done. So I'm going to go with the second one, but the first one's perfectly fine if you're more comfortable with that. It doesn't matter to me. So let's try this one. We've got y minus what? 3 equals 5 times x minus 1. And we're going to simplify, so I have y minus 3 equals 5x minus 5. So y equals 5x minus 2. So that's an equation of the tangent line to this curve through the point 1, 3. All right, so let me pause this, and we're going to... All right, so hopefully you do have a calculator with you and can graph this, because that's what my intent was to do, and it's not cooperating, but we'll manage. I'd like for you to graph the original equation and the tangent line, okay? So your original equation was y equals 3x squared minus the natural log of x. It's going to have some of the features of a log function and some of the features of a polynomial because it's a combination of the two. And then I'd like for you to graph the equation y equal, was it 5x minus 2? Yeah. And in particular, you need to make sure your graph shows up nearby the point 1, 3. That is, you need to make sure x equals 1 in your viewing window. So if you go from something like -1 to 4, 5 should be sufficient. Okay? X equals -1 to y equals, I'm sorry, x equals -1 to x equals 4 should be okay. And when you got this, you should have well, let me do this. You should end up getting a graph that looks something, I'm showing looks something like that for the first equation. Does yours look something like that? Oh, I've got some nods. That's good. So this is the y equal 3x squared minus the natural log of x. And then at x equal 1, you're somewhere like this. And I'm not going to have a good picture, but because it should be crossing at -2. Well, it's not going to be horrid, I guess. My line's not very straight, but it looks something like this. Okay. Do our graphs look something akin to that? Yeah? Excellent. What I'd like for you to see, and you may or may not be aware of this feature, and if you're not, that's okay, is the inderiv feature on your calculator to confirm. So does anybody know what I'm talking about? Have you seen inderiv before? Okay, I've got some nods. So what I'd like for you to do is out in the regular screen of your calculator, not the graphing screen, just the regular screen where you can add and subtract and so forth, is I'd like for you to pull up a feature, and that feature is underneath, if you're using a TI 8384 version, the feature is under the Math button, and I believe it's Math 8. And it should say inderiv. Do you guys see that? Inderiv? Okay, so select that one. Back out in the regular screen, you need to tell it you're going to want the equation y1. All right, so where do you get y1? Well, you hit the vars key. Do you see a button that says vars? Yep.
You
Arrow
back
over
to
to-
y after you do in derivative. Or-
After you go to derivative, you're going to hit the vars key, V-A-R-S.
Okay.
Yeah, for variables, vars is for variables. You're going to arrow over to y vars, because we have a y variable that we want. So arrow to the right 1, y vars.
Why did you go to math 8?
You hit math, and you go 8. Hit the number 8. There you go. It should say inderiv. Does it?
I have a equation.
Yours is in a different type. Let me fix it with you after class, okay? Yeah. There's a couple different types inside of some of the TI-84s that don't look like the same thing. So they do the same thing, they just do it in a different way. All right, so you get y1 by doing vars, arrow over to y vars, hit enter, and then you want function, so hit enter on top of function, and then you'll have a list of y1, y2, y3, y4. Do you guys see that? Okay, you want y1, so tell it y1. And then put a comma. There's a comma button on your screen. X, you know where the X key is. You do it to graph every time, right? X. And then what we're going to do is we're going to put in the number 1. Okay. What this is telling your calculator to do is to calculate the derivative of the equation that's in the y1 part of your screen. If you put in y1 as the first equation, 3x squared minus ln x. The variable is x, and you evaluate it at the at x equal 1 value. So this is a notation for your calculator. And if you hit enter, what does it give you? What number does it give you? So we understand that the calculator does this sort of a...
I got error.
Okay, let me take a look at yours in a minute. It should say something like this, but Taylor, do you really think it's 4.999? What do you think it really is? It's really 5. It should be 5. Why should it be 5? Because that was what we calculated for our slope when we did it by hand, right? So it should be 5. So what's the calculator doing? Well, it's not using calculus to do this. It's using a numerical limiting process. Okay, so that's why it's showing up as a kind of a funny, odd-looking number. It's 5. That's what it really is. So that gives you confirmation, especially if you were doing something that was very complicated and very messy looking, you can get confirmation that that's actually, that you've gotten the right derivative, at least at one particular point if you're evaluating, which is a nice feature. Okay, let me see the one that had the error in it. Did you get it to fix or did you not?
No idea.
Okay, well you never pulled up inderiv. You have to do math 8 first. That's what was missing.
Okay.
And this is the screen that Erica was also getting. And let me show you guys how to, after class how to change that, okay? All right. Oh, I'm so sorry.
Okay.
All right. Let's see. We have 2 more pieces of information in section 6.1 that we take a look at. Number 8, implicit differentiation. You guys have seen that before, right? What does implicit differentiation mean?
Since you can't.
Yeah, you're going to have to take a derivative of both sides. And I heard Chelsea say something about both variables and something about sometimes there's difficulty in separating those variables. Sometimes it's impossible. Sometimes it's just more convenient to leave them. And so implicit differentiation allows us to leave them where they are and to have a method for doing a derivative. Okay? So we've got a log involved here. To start with. So when we've got this log involved, what is the derivative of the natural log of whatever's next? 1 over that. So I've got 1 over xy to start. Now the next issue is that xy is a what? It is 2 variables. They're multiplied. I have 2 things multiplied. And they're actually variables multiplied, not just numbers. If they were numbers, it'd actually be easier to deal with because they're both numbers and we took their derivative, it would actually be 0. But I've got to take a derivative of 2 variables that are multiplied. How do I do that? Product rule, which we haven't done in class yet. We didn't encounter that last time in any of the pieces we were working on, I don't think. So we need the product rule of x times y. So you can do it in either order, but you need to leave one piece the same. I tend to leave the first one the same, x. And then you need the derivative of y. So what's the derivative of y? dy dx. So you can either write it as dy dx or you could write it as y prime if you're careful on your notation. I'm going to go with the dy dx so that I don't have to be careful on keeping that prime notation separated. And then I need an addition sign, and now I need the derivative of x.
One.
Just 1, right? And then I rewrite y. So I've got 1y, or if you just want to write y, that's fine. All right, so that part's done. Now what's the derivative of 5x? 5. And the derivative of 30? 0. Looks good. All right, now implicit differentiation, you've done all the calculus there is to do in this problem. Do you remember what you had to finish with when you worked on this before? Algebra by solving for dy dx, exactly. So in this particular problem, that's going to mean a little bit of separation. We're going to have to distribute something. At least that's one way to handle it. Another way to handle it, you know what, let me do it differently this time because I'm seeing something else that might be a little bit friendlier. I'm going to move the 5 first. Are you okay with that? And in doing so, I'm going to be left with 1 over xy times x dy dx. I'm going to avoid distributing, although you could certainly do so and it wouldn't hurt anything. Instead of distributing, I'm going to multiply both sides by xy. Now I have x dy dx plus y equals negative 5xy. Now what? Subtract the y. Yeah, sorry, the screen's taking a little while for it to finish showing up. So I've got x dy dx equals negative 5xy minus y. Don't have any more screen space. Now what? Divide by x. So I have dy dx equals, if you want, you could pull the negative out completely in front since both terms on top are negative. You don't have to, but you could. I'm going to leave mine put. But understand that if you were looking at a back of the book, they might potentially, instead of having this written like this, have the negative out in the very front and use addition between on top. That's a possibility. And it would be the same expression. Okay, so we kind of remember a little bit of implicit differentiation. You're going to do 2 or 3 of those in your homework. Now we're going to do something that you haven't done before, and that's called logarithmic differentiation. And the reason you haven't done logarithmic differentiation before is because you haven't worked on finding derivatives of logs before. That was an awfully insightful comment, right? Okay. All right, so we're going to use logarithmic differentiation to find dy dx, and I guess I didn't get this one written in. Our function is y equals x squared times the square root of 3x minus 2 over x plus 1 squared. And the domain is actually x is greater than 2/3 for what we're going to be doing to work. Okay, so I know that I'm supposed to find a derivative, and you have methods to find derivatives of this. I mean, you can. You'd be using some product rules and some quotient rules and some chain rules, and you'd be using a lot of mess. And to consolidate at the end would be a mess too. Now, I'm not going to contend that the consolidation in this is still not going to be a mess, but the derivatives don't need to be as messy as what you've learned before. So what do? Well, what we're going to do is we're actually going to do a step of algebra, or trigonometry, depending on your perspective, before we do the calculus. And what we're going to do is we're going to take the log of both sides, okay? So I want to do the log of both sides. Why in the world might I like to have a log on the right-hand side? Not to cancel out later, no. What is that log on the right-hand side going to allow me to be able to do? Right, to be able to separate them, to expand. So I'm going to be able to use my log rules, and then the derivatives will be much easier because I'll have simple log derivatives to do instead of this complicated product quotient chain rule thing going on. Are you following with me on that? Now it's going to look a little weird because, it is, but for right now, I'm going to leave this natural log of y on the left. And then on the right, I am going to work at separating these out. Now, I know that we didn't do a lot of this last time. We did a couple, and some of you clearly had thought through this at some point in the past, and you could move very quickly to the point where you're going to need to be. So I'm going to move quickly on this one. Noticing here that I have x squared, right? So I'm going to put the 2 in front. So this is 2 natural log of x. There's more in the numerator, so I'm going to add. Now, that square root of 3x minus 2, the square root, as we saw before today, is a 1/2 power, right? So I'm also going to pull that to the front. That's a 1/2 natural log of 3x minus 2. Now I'm going to subtract because I've got a denominator. I've still got the natural logs. Don't lose your natural logs along the process here. Hang on, though. I'm going to put a 2 in front, and then my natural log. So this 2 right here of x plus 1. That's expanded form. Okay, everybody good so far? Excellent. Now, the left-hand side aside, we'll ignore that for the moment. The right-hand side will be much easier to take the derivative of, like this, much easier. So we're going to start over there. What is the derivative of 2 natural log of x? 2 over x. Perfect. What's the derivative of 1/2 natural log of 3x minus 2? Somebody already said 1/2. Then what?
1/2, 1 over 3x minus 2 times 3.
Perfect. And then I've got a subtraction. Now I need the derivative of 2 natural log of x plus 1.
2 times 1 over x plus 1.
Okay. Or we can do 2 over x plus 1 like you wanted to originally. Yeah. And then technically times 1, but we don't need to write that. That's the right-hand side. What about the left-hand side? What's the natural log of y? Close. You've got the pieces in there, but not quite in the right order, Janet. There is a 1 over. It's 1 over what? 1 over y times dy dx. Exactly. So we actually have implicit differentiation going on the left-hand side, don't we? Because we have a function of y itself on the left, not just y equals. All right. That's all the calculus there is. It's often the case in calculus. We just use calculus at the very beginning, and then we use a lot of algebra. You guys are going to get great at it. I keep telling you that, but I'm serious. All right, so one of the things that we're going to need to do at some point is we're going to need to move that y, 1 over y over here to the other side. We need to solve for dy dx, right? So I'm going to go ahead and move it over here right now. And the other thing we're going to need to do is what? Get them all together. We need a common denominator. Agreed? Okay. So let me leave the 1 over y put for a minute. Let's do the common denominator first. At least that'll make a little bit more space for me to write. So what will I have to do in order to get a common denominator? I have to do a lot of stuff, actually, don't I? All right, so let's start with the 2 over x. What will have to happen to the 2 over x?
Multiply it by 6x minus 4 and x plus 1.
Yeah, so I need to multiply by, can I leave the 2 put? I'm going to leave the 2 right here. The 2, the 3x plus, minus 2, and the x plus 1. I'm not going to quite have enough room, but we're trying. Okay, so the 2, the 3x minus 2 give me this piece, and then the x plus 1 gives me that piece. All good? Okay. Let me move this down here because I think I'll have more space. I've got more screens anyway in a minute. All right, what will I need to multiply the middle term by, that 1/2 and that 1 over 3x minus 2 and the 3? What will I need to do with that? First of all, just for fun, I'm going to put that 3 back over here so I don't have to deal with him in there. What am I going to multiply by? I'm sorry. X and x plus 1. I didn't have to write near as much on that one. X and x plus 1. And the last one? X and 2 and 3x minus 2. What a mess. I think I could at least put this back up here. Just going to keep moving things around until they land where I want them to land. Okay, we're going to simplify, but we are not going to simplify by multiplying out the denominators. The denominators are going to stay put in factored form, okay? Okay, so the numerator on the first one, what am I going to get? Well, it's probably going to take us a couple of steps, but right now I've got 4 times, let's multiply this out. 3x squared, then what? I have negative 2x in the middle and positive 3x on the outside, so that's plus x, right? And then minus 2. Okay. Oh, down here it's not so bad. This is a 3. So I've got 3x times x plus 1, which gives me what?
3x squared.
Perfect. 3x squared plus 3x. Down here I have a little bit more going on. I've got a negative and I've got 2 2's. So I'm going to, well, and I've got this x. This is negative 2x right here. Times the 2, so this is negative 4x. So let's just distribute that negative 4x through. So negative 4x times 3x would be negative 12x squared, and then plus 8x. And my denominator is going to have a 2x times 3x minus 2 times x plus 1. It's not going away, I promise. All right, we'll distribute the 4 through, and in fact, I think I'll do it above that, and then we can actually combine them so that we don't have to have another separate actual step here, so that I can conserve a little bit of space. So if I combine the top, I've got 12x squared, not to combine, but multiply 12x squared plus 4x minus 8. Now we need to combine. All right, so x squareds. How many x squareds do I have? I do. I just have 3x squareds, right? Because I have 12x squared at the beginning and a negative 12x squared at the end. How about x's? 15? Yep, 15 x's. How about constants?
Shouldn't that be a negative 9x squared?
Oh, which one of them?
Like you have 3x squared plus 15x. Up there you have a 3x squared and a negative 12x squared.
But I had a 12x squared at the beginning. In red.
Oh, okay.
That 12x squared at the beginning and this negative 12x squared at the end. So it does end up leaving the 3x squared, yeah. All right, so I had 3x squared, I have 15x, and then I have a constant at the end of what? Negative 8, right? There weren't anything else to combine with them, were there? I don't think so. It's almost like cleaning house. When you get to this point, you go, because it looks so much better, doesn't it? Way better than when we started, for sure. At least at the point when it was all not multiplied out. Now, we'd mentioned this before, and I said, let's just hold off. We've got this 1 over y on the left, and I want to move it to the right-hand side as well, so I can multiply simply by y to the other side, correct? There it is. So I'm going to multiply by y on both sides. But what is y? think it's x squared square root of 3x minus 2 over x plus 1 squared, wasn't it? Yeah. That's what's got to go in there, not y, because I know a way to write y in terms of x. Now, occasionally you don't have a way to write y in terms of x, but on this one we did, so we will. So we're going to take a look at doing that and simplifying if we can on some of that, and we can on some of it. So we've got the original piece in red there. We've got my 2x, 3x minus 2, and x plus 1. And then we have y. And y included x squared. I'm going to write the square root as a 1/2 power. We already talked about that anyway. And I've got x plus 1 squared. All right, so simplifying, cleaning up, what can we do? Well, we can't exactly cancel them out, but we can combine them. How can they? Because they don't actually both have the same exponent, right? One of them has a 1/2 and the other one has a 1. So how can we combine them? Yeah, subtract the exponents, right? So if we subtract our exponents, hang on. Oh, we'll just leave it. I would get that same 3x minus 2, it's on bottom. How do I know it's on bottom? Because it's the bigger exponent. And what will its new exponent be? It'll be positive 1/2. In essence, this is 2 halves on bottom, and this is 1/2 on top, so one of the 1/2s is going to cancel, leaving a 1/2 on bottom. That's one way to think about it. Okay, so that takes care of one of the pieces. So Janet took care of that one for us. What else can I take care of? Does anything legitimately reduce? One piece legitimately goes away. I can get rid of an x. Not an x squared, but an x. This x right here and the squaring right there, in essence one of those two that's making that squared, can go away. So I actually will be left with only one x, and it will be on top. So let me do this to this, and it'll leave me one x on top. The 2 is going to stay on bottom because it doesn't reduce on top with anything. How about those x plus 1s? They don't reduce, but they do combine, don't they? What can I write? X plus 1 cubed. It's not very good cubed. Let's try again. All right, and then I can distribute the x that I just got in red over here through to the 3x squared minus 15x minus 8, which doesn't happen to factor. And if you wanted to try it, you could, but in this particular case, it won't. So we can either distribute through or really keep it in factored form. Your book would probably distribute this through so that you would see this written as 3x cubed plus 15x squared minus 8x. The other thing you might see is instead of it written as a 1/2 in the denominator as an exponent, you might see that written as a square root. And it is okay to leave square roots in the denominator because this is the square root of a variable expression, not a number. So that's fine. You can leave a square root with variables in the denominator. Any questions on this one? This is sort of the culmination of all the pieces of that section, right? Including the implicit differentiation, the log rules, and all of that, and all the algebra that you're bringing to it.